Hi, and welcome back to another video with It's Dr. Dan, and welcome to my practice problem series. So with practice problem series, we're going to go through some more advanced problems to help you solve your general chemistry homework and try to figure out different problems that are combining different concepts found throughout my videos and those from your classes in chemistry. So this one, we're going to really be focusing on how equilibrium and solutions and molarity are all going to be mixing together in practice problems. So we're going to be going through a series of 3 different major practice problems that are going to be varying in difficulty from introductory chemistry to all the way to general chemistry 2, just so you can kind of see what some of these are going to be coming across. So there are a lot of different types of problems that you can come across in these, but the biggest ones are really going to be calculating K values, so those equilibrium constants, whether it's KEQ, KC, KA, KB, KSP, right? There's all kinds of these. The other thing is looking at, all right, based on that value, what side of the reaction does it favor? Is it reactant focus or is it product focus? And that has to do with the K, how big or small that K value is. The last thing what we're going to be really looking at is writing solubility products, which is KSP, which really sees is something soluble when you throw it in. So if you take a solid, you throw it into a solution, does it break apart? And we're going to actually go through a general chemistry 2 concept, which is a preview of future videos that will eventually come in the years to come. So other videos that one other question we're going to look at is calculating concentrations at equilibrium as well. So how can we try to look at these problems and calculate a concentration? So if you're trying to figure out, if you only are interested in one of these problems, don't forget you can use a little scroll wheel down below with the labeled chapters to find your practice problem. They are labeled for you to easily find them. Hopefully this video helps, and stay tuned, and please hit that like and subscribe button for future videos on different topics and for future practice problems. So thank you for coming here, and let's get to it. All right, let's get at it. So the first problem, at equilibrium. So with this problem, what we are looking at is we have 2 sulfur dioxide reacting with oxygen gas to yield 2 sulfur trioxides. So what we have is that the amount of each gas was measured, meaning that at equilibrium, we are able to do that in the lab. So we have the following concentrations of 0.35 molar of SO2, 3.25 times 10 to the negative 1 molar of oxygen, and 6.41 times 10 to the negative 2 molar of SO3. So it says calculate the KEQ. So if this is something that you weren't too sure about, go back to the equilibrium video so we can set up these. But just in brief, the one thing that we're looking at when it comes to K equations is it's all about products over reactants, meaning that we are going to be looking at the concentrations of these, and we are going to be raising those different values by their coefficients to their powers. So let's look at this one in particular. So if I'm interested in doing the KEQ for the following problem, well, we have our products, which is sulfur trioxide, so SO3. And for that one thing that you may notice is that it has a coefficient of 2. So what that means is that we are going to raise this to the power of 2 to illustrate that it has that coefficient. So that's going to essentially square its potential of colliding with other SO2s in this reaction. We have our reactants, so we have SO2, and then we also have oxygen. And one thing you might be kind of yelling right now, you're maybe yelling at your monitor, is like, oh, wait, there is a coefficient for SO2. So let's do that. We are going to put that to a power as well. So that is what I was mentioning, is that we need to raise these by their coefficients when we are writing out these values. So the problem calls for calculating its K value going through this. So when we are trying to calculate this, what we need to do is take our values and plug them in. So SO3 is 0.641 molar. Then for SO2, we have 0.35 molar. So let's just highlight those in the problem to help us see that. So SO2 is here. And then we have SO3, which was here. And then our last one is going to be oxygen. So we will put in our oxygen value as well. And that is going to be 0.325. And that's going to get plugged in as well. Then we got to raise our SO2 to a power. And then we can calculate KEQ. So we'll plug these into our calculator and then we will solve it. Get for KEQ is a value of 0.10 as our value. And what we need to go off 3 sig figs in all of our values. This is going to be a value of 0.103. So what does that tell us about looking at this? Well, if you remember from my previous video on equilibrium, K can either be greater than or less than 1. With that, it tells you what the ratio is of the concentrations. So if K is less than 1, that means that it favors the reactants. If it's greater than 1, it favors the products. So in this situation, it's telling you that based on this reaction that we have, this is greatly favoring the reactant. So it's favoring the left side of it, meaning that there's more SO2 and oxygen once this equation or this reaction is at equilibrium. So this is one thing to look at for this problem. On to the next. Okay, let's do it. So this next one is what we are trying to do is look at the following thing, which tells you write the net ionic equation for the solubility of copper hydroxide, which what this is trying to set up when it comes to equilibrium is telling you that if I have a solid, let's say kind of like table salt, right? So which is something that you just put on food every day. If you are to have that in your hand, it is in the form of a solid. But if you throw it in a glass of water, quickly in a blink of an eye, it will dissolve and vanish before your eyes. This is what this is trying to ask you, is if I have something like copper hydroxide, where this is a copper salt, which is a solid, what would happen when that is thrown into solution? When it goes in, it's going to dissolve into its most basic ions. So the first one being copper 2+, and the other one being hydroxide. But being that this is OH minus with a 2 here, we don't write OH, we don't write that there's OH minus with a 2 subscript. We are going to show that as a 2 coefficient to say that, oh, this is breaking down into its most simple ions when this is in solution. So being that it's breaking down in water, these are all considered to be aqueous as we write what is referred to as the solubility product. So that is what these are on the right-hand side. These are all solubility products as these are dissociating and being ionized by water in solution. So the next part is asking, all right, write the solubility product equilibrium expression, which is a little bit of a mouthful, but what that's asking for you is a different form of K, which is still products over reactants, but it's KSP. So when we are writing our expression for KSP, we still do products over reactants. So we have OH minus as one product, and that's going to be raised to the power of 2. And then we have a coefficient of 2. And then we have copper 2+. Now, the reactants is copper hydroxide. But one thing you might remember is that one of our rules is we never write solids or liquids. So being that we never write solids or liquids, we do not include it in this portion of the problem. So this is going to be our equilibrium value. It stays the way it is. So we can kind of box that portion off, and that is our equilibrium expression. So based on that, let's say if I ask you the following. If the KSP of this solution is 1.6 times 10 to the negative 19, is copper hydroxide soluble? Well, what do you mean? Didn't we just do a whole entire solubility expression? Well, based on the K value, that tells you how soluble is something. Is it soluble, or is it relatively insoluble, or partially? So this gives you an idea of if you look at the reaction, 1.6 times 10 to the 9. First, you're going to ask yourself, is that greater or less than 1? And one thing you're going to kind of see is that, oh, K is very much less than 1. It is very, very small. So when that happens, that's telling you, if I go back up to my reaction here, that this is very much favoring the left-hand side of the reaction. So being that that is favoring the left, that's telling you it's mainly existing in the form of a solid. So this expression is not very soluble at all. In fact, it's 10 to the negative, that's 19 orders of magnitude away from 1. So you can probably say, no, it is not soluble. This would be a big no. This is insoluble. So on to a more advanced concept. If you're just here for introductory chemistry, there's some little math skills that might be useful here that are worth watching. But if you're not here for this, this will not be an introductory chem class. This will be in general chemistry too. So let's try to make this one step farther. If I ask you the following, if I have, based on the information that we had before, so the KSP was 1.6 times 10 to the negative 19, we know that it's equal to copper in solution times hydroxide in solution. So what if I ask you what is the copper concentration? How would you figure that out? Well, we have all the pieces of information that we need. And how could that be? Well, one thing that we can do is that these are all particles that are all pretty hard to tell apart, right? All particles are really tiny and they're indistinguishable based on the theories that we've looked at in the past. So and this is a basic general chemistry assumption we like to make often. So if we say that where every one of these ions, let's say if I have copper, which is an ion, I also have hydroxide, which is an ion, what we are going to do with them is all assume that they all equal just a common variable that we have in math. We'll just call it X. So what we will do is if I have KSP and I plug in X for copper and for hydroxide. So now I have X times X squared. And all of that is equal to 1.6 times 10 to the 19. Well, based on algebra, this is something that you can simplify. Being as X times X squared, multiply these two things together on both sides. So when that happens, we can simplify that to be X cubed. Okay, so being that this is now X cubed equal to 1.6 times 10 to the 19, how can I get X by itself? Well, the way that we can do that is we can take a cube root of this. So instead of a square root, it's a root with a 3 power instead of each side. And what that's going to do is cancel out our cube on the left side. So that's something that you can just plug into a calculator when you do that. And when you do that function, that's going to tell you that X, which is the same thing as copper, the concentration of that is going to be equal to 5.4 times 10 to the negative 7 molarity. Okay, so and that's going to be your copper 2 plus concentration. So this is something that if you're taking future classes, that's a future concept. On to the next. Okay, let's do our last practice problem for this set. So the Ka of the following reaction is 1.6 times 10 to the negative 5, meaning that we have a reaction of acetic acid, so CH3, COOH, and it's reacting with water to create H3O plus and CH3COO minus. So what we are seeing is an acid donating its proton to create hydronium, and it's making a conjugate base as well. So what we have is we have the reaction, the Ka value, and we have the concentrations of acetic acid, which is 2 molar, and we are given the concentration of CH3CO minus, and that is 0.25 molar, and this is at equilibrium. What is the concentration of hydronium and determine its pH? So this is combining equilibrium with acids and bases all together. So how do we start it? The first step is being that we already have a balanced chemical reaction. is for us to write out the equilibrium expression for Ka. So Ka is going to be equal to the products over the reactants. So we have H3O plus, then we have CH3, COO minus. In our reactants, we have CH3, COOH, and we also have water. But one thing to remember is we do not include water because we never include solids or liquids. So this will be our equilibrium expression. Now, from that, we were given a lot of different values that we can plug into this. The first one from above was the Ka constant for this formula. So we can plug that in. So Ka was 1.6 times 10 to the negative fifth. So when we plug that in, we can now take our formula and plug in all the concentrations. So H3O plus is our variable. We're trying to find that. We can plug in the concentration of CH3COH. So that was 0.25 was that value. And then we also had our concentration of acetic acid, which was 2.0 molar as our value. All right, so what are we trying to do here? Well, we have to get H3O plus by itself. So how do you do that? Well, this is all an algebra problem. So the first thing that we're going to do is to get this by itself is we're going to multiply 2.0 by both sides to cancel out the 2.0 on the bottom. So that would be step one. When that happens, 2.0 gets by itself. We can simplify our number now on the left. So that would be 3.2 times 10 to the negative fifth is equal to hydronium plus and 0.25, which that was in blue before. So let's put that in blue again. So let's put that in the same size too. That's 0.25. Now, how do we get hydronium by itself? Well, being that they're both being multiplied by each other, the way to get them separated is by dividing them. So if we divide those two values by both sides, so if I divide it on the left and on the right, we will get that value by itself. So 0.25, these cancel out. We'll do the same thing on the left side. Now what that's going to do is give us our concentration of hydronium, which will be 1.28 times 10 to the negative 4 molar of hydronium. So that's our concentration. So that is one answer. Now, if you remember from the problem, we also had to figure out pH. So how do we do that? Well, that goes back to the pH and acids and bases video, which the way to solve for that is, if you remember, is that pH is equal to the negative log of the hydronium concentration. And one thing as a tip, if you ever see hydronium, that concentration is going to be equal to what you see for hydrogen ion, depending on how a problem is being written. So another little tip for a practice problem. So when we have this, we're going to plug our value in to this equation. So the 1.28 is going to be plugged into this value. So when we do that, we are going to get a pH of 3.89 when we take the negative log of 1.28 times 10 to the negative 4. This is my last practice problem. I hope this video helped going through several different examples. If these helped, remember, this is Dr. Dan here. Please hit that like and subscribe button to see future videos, and I hope that I can help you pass and ace your chemistry class. Thank you so much for stopping by, and I'll see you all later. Bye now.